welcome back to the simulation practice. Uh, in this video, you would be designing the wind energy conversion system using 1.6 kilowatt permanent magnet synchronous generator. This is the final structure of the simulation circuit. So, we'll see how to design it. It's very simple and you have the wind turbine model and followed by the PMSG generator. Then you have a load. We are calculating the efficiency based on the power output, and here during the runtime we would be changing the wind speed, and based on the wind speed we will study the characteristics of speed versus power through this graph, and we would also see the output power, how does it vary with respect to the other parameters, and the efficiency also. Okay, so let's get into the practice session. So let us open a new Simulink model where we need the wind turbine. So I'll take it as wind turbine. So it comes as this. So this is the wind turbine. You could see the generator speed, pitch angle, and the wind speed as the input, and we can get the output from the wind turbine, which is as a torque. So that torque will be required for us to drive the generator. So this wind turbine refers to, that's the model how the torque is developed. That is, this converts kinetic energy to the mechanical energy. So in the form of torque. So your kinetic energy, especially the wind speed, which is an input to this, and then it gives back the mechanical output as a rotation in the form of torque. So this is the wind turbine. So we are not much interested in modeling these things, but some of the parameters like you have the power output, what you require here by default is given as 1.5 megawatt. So for us, we are interested in 1600 watts. So I just replace this 1600 and this also I keep it as 1600. This is the per unit value of the base, that is the base power or value. So per unit is zero point 0.9, so the base power becomes 1600 divided by zero point 0.9. The wind speed is 12 meters per second, that I'm not changing any of that here, and the rest of these parameters remain the same. So we are just changing the power, what is our requirement. So you can, so if you have need a different power requirement, you can change that. Okay, so the next one would be the generator. So I need permanent magnet synchronous generator. Yes, here. So this is the permanent magnet synchronous generator. As just a machine, we are going to design, or we are going to change it to the generator. So as of now, I required as a generator. Just I'm um, flipping the block so that I get the output in the right side. Okay, so this is 1.6 kilowatt PMSG, permanent magnet synchronous generator. Okay, so this is the, but and we can directly connect the torque, which is the output of the wind turbine, to the torque of the machine, so that it will be easy for us to drive it. The output of this PMSG wind turbine is what we require. So because this converts your mechanical input to the electrical output. So the output of this, we need to measure the electrical parameters. So we'll take the bus selector. So in the bus selector, I'm just connecting it with the output. The measurement port, I'm connecting it, and now we got to select the measurement port. Double click the bus selector. We could see, we'll remove this, and we have many of these things here to measure. So as of now, for this measurement, we would take the rotor speed and the electromagnetic torque, that is the machine torque. Okay, um, select it, push it down. Okay, now apply. Okay, so now it is taken. Okay, so now we have to take an in, I mean, like the load has to be connected to here. So I'll use three-phase load. I'll take that. Yeah, three-phase. This is the three-phase load, and we have to set the values related to our requirement. So this by default, I'm just fixing to the output RMS voltage as 400. The frequency is 50. Now the active power is 110 watts. You can either change it to different values as your requirement. Okay, now just so this is we are not going to do any load test here, so I don't want to be more specific on the loads. I want to also measure the current across each thing, so I'll use current measurement. Okay, I can either use the three-phase current measurement system, but I just want to do this, use this because I need to fetch more details. Okay, so connecting the ammeter across through all the terminals. The line we are measuring the line current in this, right? So we have the line measurements to be done. Then we can also measure the voltage through the voltmeters. So we have this voltmeter. I can connect between A and B. So this is the line voltage. Then I connect between B and C. Then I connect C and A. Okay, so we can get this. So to measure the power, I need to multiply the voltage and the current. But since we get a sinusoidal the output from these meters, I need to convert to RMS values. So I check the RMS, check this inside. Okay, we need to change it to 50 hertz. Okay, so we have to change it to 50 hertz. I just want of the one of the measurement. Okay, so I connect to this and I take another to measure the voltage. Okay, measuring this out. So this 2 RMS has to be multiplied, so we need the product to measure the power, and we can get the output from this. So to not to because these are the AC terms, we need to stabilize it. Let me put some active filter, analog filter. So I keep by default this as a filter order is 2 and this is 100.5. Okay, so I connect it to this and we get the power in watts. So it would be for the measurement and the comparisons, it would be much better if I could change the power value to kilowatts. So I put gain and just multiply the output by 1000 so that I get in kilowatts, right? Okay, this is the part where we are going. So then we also have the other measurements to be done, that is the current and the voltage. So I'll take the mux. I'll make the mux as 3 inputs. So because I'm going to measure the voltage, sorry, now the current. So I'll take the first phase, second phase, and the third phase here, and this let it to be connected to a scope. It's not connected here. yeah, to the scope. So I'll make it as 2 axis. So you remember to, like, if you are changing the input port here, it is must that you need to make the layout change also. So that it will be only then the two ports will be displayed. Okay, hope you remember that. So now I have two things here. One, I give it to the current, the other one need for the voltage. So again I copy the mux for the voltage. So this is for phase 1, this is phase 2, and this is phase 3, and now I connect this to the second. So okay, so now in this scope we would be able to get both the current and the voltage waveforms. And okay, so now then let us calculate for the next one. Like, I need a graph on the input parameters. So I'll take another scope. I would like to compare the, so before, let's see this way. We haven't given any input to this. So I need to have a constant. So I connect it, and also I connect this and speed. So in this, the generator speed per unit is per unit value is taken as 0.2. The pitch angle remains 0. We are not going to do any pitch control here. This constant, which is nothing but, I'll rename this as wind speed in meters per second. Okay, so I want to put this value, or the blocks should have a variable nature, so I'll put knob. Okay, I take this one, quite easy to handle. I'll now link it, so I'll click the connection and I'll select this one. So now the wind speed value would change based on this. So I'll keep it the value from 0 to maximum of 40. Okay, have 5. Let's see, yeah, I can have 5 duration. Now this is connected. So whenever you change the input here, the wind speed change, so that we can have a dynamic environment of simulation. Okay, now I also want this electromagnetic torque and the rotor speed to be measured. So I put it here. Now, once the power is calculated, I want to I need to compare it, one with respect to the power versus wind speed. Okay, so what I do is I will take the wind speed to study this. I need a wind speed curve to be also seen, followed by the power output that also is required. So I'll take it from here. Right. So, and also I would compare the, I'll also see the turbine characteristics. So in order to study the turbine characteristics, I need to take two things. So one is I need to compare uh, the electromagnetic torque and the radius, that is the rotor speed, and also I need to measure the wind speed. So these all comes into it. So if you want, you can have it. So you can, already it is measured, but if you want to have a separate wind turbine characteristics, you can do that. And also we need to find the wind speed characteristics. So I take XY graph. In the XY graph, the x-axis, it should be the wind speed. So I take, where is the wind speed? Yes, it's here. So it goes to the first, because the x card, and the power that is measured, it will be in the y-axis, so that I can measure the wind speed characteristics. So I'll rename this as wind speed characteristics. All right. Okay. So let us also calculate the efficiency. To calculate the efficiency, I need to uh, I need the input power, so I take constant which we have fixed for the input power as 1.6 kilowatt, that is 1600 watts. So this is the input power, and we need a divide block. So it then in the numerator we need to put the output power divided by input power. So we get this, and also this is for the efficiency. So I need to multiply by 100, so I get it in percentage. Okay, so also I will put it. I need a graphical representation, so I will put the graph. One is the efficiency, the other one is the output power. Okay. So just simple as that. We have almost done it. Okay. So now power GUI. Okay, it's in continuous. We don't have any discrete model here. So this is just the simple. So very simple model that how we are going to study about the wind turbine and the so the stop time. Since we need to measure for a long time, changing it, I change it infinity. Okay, so it will keep on run until you stop that. So these are the parameters that is used here. So let's now simulate this. So for initially we have kept the wind speed as 0, and we'll see what are the terms that are going to change. So I'm going to run it. Okay, so now it has started to compile, and the simulation starts. So from 0, I'm just moving this to change the speed in order to get the variable speed. So up to 40. So now I stop it. Okay, so now let's see how the curve has come. So first thing is the wind speed and the power generator. Let's see on this. Just auto scale it. Okay, so I'll just zoom it, zoom this. Okay, you can see how we have changed it. So from this terminal, the wind speed has slightly increased, and you can see this is where this is the wind speed reaching about 10. Okay, so this point maybe 5, and after that very slightly the power has generated, and since the base speed is 12 meters per second, the actual power is generated. So from here, and it rises, but the wind speed is keep on increasing. So it is understood that at a certain level the power would drop. That means the cutout speed has reached, so it drops, and we are in a continuous simulation model, so it continues in the per unit value of the output power. So this is that, and when you come to the turbine characteristics, also we can understand this. We can see this. I'll cover the last. Yeah, this is the turbine characteristics. We can see the generator torque here. So this blue line is the generator torque. So would like to see how much is the generator torque. Okay, the torque is being fluctuated upon driving it. So this is what, and if you see the rotor speed, I'll zoom this way. You can get the same. Okay, so rest of the things is already seen in the previous graph, and have the efficiency, or before that we need to see the voltage and the current. Okay, so we have the first one, the current is here. So until this point, the it's in the zero speed, so it is not generated. So after which the wind turbine starts to generate electricity. So you can see, and the different nature of the curve amplitude being changed here. That is the due to various change in the uh, this wind speed, and so you can see this. So you can see the nominally the voltage is voltage and the current are changing in its amplitude for the different uh, wind speed. And now we'll see the performance, the efficiency. So the efficiency also drops uh, once the cutoff speed is reached. So we, since it's a 1.6 kilowatt generator, uh, the power also should by reaching to the 1.5, close to 1.5, we will be able to reach the uh, actual, that is the, we will be able to reach the maximum efficiency that I could, right? So now the wind speed curve, if we check the wind speed curve, it will look very nice to see that. Yeah, I can see that. This is the multiple plot. So as you know that the wind speed is taken in the x-axis and the power is taken in the y-axis. So in here the wind speed after 12, like it's going to start from here. The power is getting generated only after 12 because that's the base speed we have kept. It slowly increases as the and the maximum power is reached at, you say, between 21 meters per second to 25 meters per second, after which it drops, keeps dropping up to 40. So after which there is no power generation. So this is the cutout speed so for this generator. And this is how the total the overall wind characteristics can. So this is very very simple simulation model. You can change the power rating, and based on the power rating you would be able to study the various characteristics. Here some of the gain terms are used, so that is for the comfortability of including the load values to the current directly, because we are not doing any load characteristics. So I hope you all can practice this. That will be helpful for you. Thank you.